My name is Dax Hamilton. I founded a company called Dax Ham Laser Solutions, and I provide consulting and related support and services surrounding laser plastic welding technology. This part in the series is called the 4 Pillars of Laser Plastic Welding, and we cover basically the 4 main parts. If you know these 4 parts, you're almost on your way to designing in laser plastic welding. First pillar, transparent upper layer of plastic. Okay? This layer needs to be transparent to the laser wavelength used. Okay? So typically for laser plastic welding applications, we're using lasers in the wavelength spectrum basically of 980 nanometers or around 1 micron. Okay? And basically the plastic, this transparent layer, which is typically the lid in the case of a lid to a housing where electronics are contained inside, this needs to pass that laser wavelength. Okay? It can be opaque. That means it can be colored, whether it's black or green or blue. It really doesn't matter. But as long as that dye or that pigment is able to allow a certain amount of the laser energy to pass through, because we need to get down to the base layer in order to get laser plastic welding to happen. It needs to transmit about 5% or more of the laser energy. You can check this with a transmission checker that some of the suppliers build. You can check it with a laser power meter, basically inside your machine, put the plastic over the top, set the laser to 100 watts, shine it through, see how much your power meter's getting. There's a couple ways to do it. Or you can have one of the suppliers check it, material suppliers, present guys, so on and so forth. Amorphous materials work very well. Semicrystalline materials and crystalline materials can be welded, but it's on a case-by-case basis. The second pillar is the absorbing layer. Okay? Typically it's the lower layer of the plastic. This, in my opinion, is the most important layer. It needs to be doped with an IR absorbing material, typically carbon black, in a range of about 0.2 to 0.5%. Now, if you want to do other colors, you're going to have to experiment. I mean, the resin suppliers, RTP company, others like this, can actually dope the base layer so that it absorbs the laser energy, but it doesn't have to be black. So typically with parts that are gray or black, you have carbon black in them. If you want white or green or blue, a lot of times titanium dioxide with other compounds are mixed in to absorb that laser energy, but to allow a lighter spectrum of colors. The energy is absorbed and transfers heat to the upper layer. Thermal expansion of this layer causes mixing. So what happens is, as the laser heats the base layer of plastic up, as long as there's good mechanical contact between the two, heat transfer will happen, thermal expansion will happen and actually melt and mix those materials. So it's literally forcing a little bit of the lower layer up into the top layer. You can color match to achieve virtually any color desired. So upper layer, lower layer, really doesn't matter. It can be green, blue, orange, pink. This just depends on which compounds are doped into the material to allow for transmissivity and absorption. The third pillar is mechanical contact. This is the most critical factor in order to obtain a stable laser welding process. I've seen so many times in the industry where clamping is subpar, substandard, and it allows for warps or twists or gaps, and your part is not going to weld. Just the bottom line. What's going to happen is if there's a gap between the upper layer and the lower layer, you're not going to get any heat transfer because there's no mechanical contact. What's going to happen is the laser is going to shine through the transparent layer, get absorbed into the lower layer, and burn and turn this lower layer to carbon before it can transfer the heat to the upper layer and get a stable process. Very, very, very critical that the clamping is designed right, no gaps, holds the part tight while the laser welds. Again, no gaps in between the layers of more than 0.05 millimeters. The parts must be able to handle the clamping forces. This is very important as well. You don't want any buckling to occur as you apply that clamping force. This is especially true with large microfluidic parts where there's a lot of weld rib. You need a lot of force on those. Okay? Around 2 to 3 newtons per square millimeter of weld rib surface area. Proper support into the weld area to avoid buckling. Basically, everywhere that we're actually going to weld, we need support in that lower fixture. And the part needs to be able to transfer those forces from the top down through the walls, or however the part is configured, and allow it to sit on that fixture tight. The fourth pillar basically is material compatibility. This is really critical. It sounds maybe more complex than it is. The bottom line is that like thermoplastics weld very well to themselves. Okay? polycarbonate to polycarbonate, PMMA to PMMA, so on and so forth. Okay? And you can see a chart here by Evosys Laser Solutions that basically kind of depicts some of the common materials and their weldability with themselves and with other materials. Okay? Dissimilar plastics, separate two different types of plastics, must have an overlapping process window in order to weld. Okay? This is basically a couple things here. Glass transition temperature to decomposition temperature. So when, let's say, glass transition temperature where the plastic just starts to soften and melt, okay? And then the decomposition temperature is where the plastic would degrade and or turn to carbon, okay? So we need to have this window overlap with the other window of the dissimilar plastic by about 50 degrees C. The bigger the window, the more stable the process, okay? The next thing is that the molecular structure must be compatible, okay? So for instance, you couldn't weld a silicone into a polycarbonate. I'm not gonna get into materials science here, but the bottom line is that these two dissimilar materials need to have a similar chemical composition or similar makeup in order to bond well with each other. Okay. So pretty much that wraps up our 4 pillars of laser plastic welding. Personally, I feel that if you know these 4 basics, you're going to be able to design your part quite well and really avoid any issues or common pitfalls, which we'll cover in a later section. Thank you very much for watching and look forward to the next